Hello, everyone, and welcome to the last day of the conference. Today we have Dan Fried from Harvard speaking about anomalies and quiche.
Thank you. It's always a delight to be back in Oxford and see old friends, and also to be at this conference. So I will talk about joint work with Colleen, Julia, and Constantine, but that will come at the end of the talk. And I will give some general remarks about starting with anomalies in general in both quantum mechanics and quantum field theory, then talk about anomalies associated to groups of symmetries, and then talk about algebras of symmetries as opposed to groups of symmetries, and finally come to the central question about what it means to have anomalies when we have algebras of symmetries. Okay, so here's the slogan, my slogan about anomalies, which is that quantum theory is projective. Rather than a linear theory, it's a projective theory. The second half says quantization is linear. That won't enter into this talk. We won't be talking about quantization today. And what the anomaly is an expression of the projectivity, which is the obstruction to linearizing something projective. That's the general description of what an anomaly is. Notice that anomalies are not necessarily associated with symmetry, although they're often presented that way, nor are they particular to systems with fermions. They can happen in systems with only bosons. So usually when we talk about quantum mechanics, we say the data is a Hilbert space, a linear space, and a one-parameter unitary representation of time translation. And that's the data of a quantum mechanical system. From that, you derive states and observables and so on. But you can derive all that instead from a projective space. You don't need to have a linear space. You can have the underlying projective space. And as I said at the top, the anomaly is then the obstruction. It's the thing you have to trivialize to linearize that projective space. So for a single family, for a single system, for a single projective space, of course, it's not very interesting. There's not much there to linearize. But if you have a family, or if you have a system with symmetry, then there's something. So here, it's a depiction of a family of projective spaces. And we can ask to linearize it. To linearize it means to find a vector bundle, a bundle of linear spaces, and such that the underlying, the associated projective spaces of those linear spaces are your given family of projective spaces. In other words, we need an isomorphism. We need an isomorphism between the original projective spaces and the projectivization of those linear spaces. So the obstruction is what's called a gerb. It's, in a sense, a once shifted or once categorified version of a line bundle. And a line bundle itself has an interpretation in this context. It's a family of quantum systems where we have of linear quantum systems where we have one-dimensional state spaces. So those are what we would call invertible quantum systems. So already in quantum mechanics, just with a gerb, you see that the anomaly is a once shifted or once categorified variant of an invertible system. Okay. We could also have the family being a single system, but with a symmetry. So here we have a point, but a group G acting. And we could have, again, a projective system, which means we have a projective representation of the group. And then we could try to linearize, which means make a linear representation of that group. And of course, in general, you can't do that. You might encounter a central extension of the group. And that's the typical case, that something centrally extended gets represented linearly. And linearization is the same as splitting that central extension. So a typical example already occurs with the harmonic oscillator in quantum mechanics. Okay, so when we come to quantum field theory, we're going to work in the Wick-rotated setting using the axiom system that Graham-Siegel introduced long ago. There are two discrete parameters that tell us what kind of theory we have. One is the dimension, which is the dimension of what would be space-time were Wick rotated. The other one is the background fields. So the background fields are something that you define on every smooth manifold of dimension n. And if I have a map of manifolds that's a local diffeomorphism, we can pull back fields. So for example, a Riemannian metric is a possible field, and it pulls back under local diffeomorphisms. So do things like orientation, spin structures, etc. And they obey a sheaf property, which means that they're local. That locality is, of course, at the core of quantum theory, quantum field theory. So Graham's axiom system says that we take and make a Bordism category. These Bordism categories, by the way, in topology were first introduced by Milner in the 60s. And we make a Bordism category where the objects are closed n-1 manifolds, and the morphisms are Bordisms of such closed manifolds, so they're compact manifolds with boundary. And each of these is equipped with a background field. So this field is an n-dimensional object, so these boundaries are thickened a little bit to n manifolds. And what the field theory is a linear representation. If we have a linear field theory, it's a linear representation of the Bordism category. So the objects get replaced by vector spaces, usually infinite dimensional topological vector spaces. And these Bordisms get mapped to linear maps of those topological vector spaces. So I want to emphasize that I'm not talking just about topological field theory. These are general axioms for field theory. So according to the maxim I put on the first slide, a quantum theory is supposed to be projective. So what does that mean in this context? Well, we shouldn't associate a linear space like this to each Bordism, but rather we should associate some sort of projective space. So instead of mapping to a category of vector spaces and linear maps, we should map to some kind of category of projective spaces. And there is such a category. I won't spell that out in detail. The recent papers by Jackson Van Dyke that work that out in detail. But basically, you want to take the quotient of vector spaces where you identify two vector spaces if they differ by tensoring by a line. So we think of the category of lines as being some categorified version of a group. It acts on the category of vector spaces by tensor product, and this is a quotient. That's the rough picture. So a projective theory, then, is a map from this Bordism category to projective spaces rather than to linear spaces. Well, if we look at this sequence where we have these lines acting on vector spaces and then this quotient, lines is something abelian, tensor product of lines commutes, we can make some kind of classifying space or shifted version of that, which is what projective space is mapped to. And in fact, you should think of this as being made up of gerbs, and a projective space maps to the gerb, which is the obstruction to linearizing. So if you take a projective space, you map it to the gerb. If you linearize, you trivialize the gerb, that's the same as lifting the projective space to vect. Here we're doing it all at once in a theory, not on a particular manifold. And so if we have a projective theory, we can compose, and that is the anomaly then. So for example, to each object, a closed n-1 manifold, it associates a gerb. That's the obstruction to linearizing the projective space given by that theory. Well, as I said, in the case of groups, you can think of that projective representation as defining a central extension and a linear representation of that central extension. And then a trivialization is, well, it's a lift of this map, this projective theory to a linear theory, or equivalently, a trivialization, splitting of this central extension. And notice if we have ratios of splittings, then those, as usual, are homomorphisms from the quotient to the sub, which here would be a map from board N to lines, and that's an invertible field theory. So you see that the anomaly itself is, again, a once-shifted or once-categorified version of a linear, of an invertible field theory. That's how the anomaly comes to us. If we go back to central extensions of groups, if we had a finite group, then you might know that a central extension is given by a cohomology class in H2 of the group with coefficients A and C star. Well, that's one shifted from H1 with coefficients in C star. H1 with coefficients in C star are homomorphisms from a finite group to C star, which is to say characters, which is to say one-dimensional representations. So,
I have a question.
yeah.
So this is like the kind of way to characterize anomaly in flow, no, in quantum field theory, like you have an SPT in one dimension higher, no? But does this also work for like non-invertible symmetries, like when there is no group structure?
Well, we'll come to algebras of symmetries, yeah. Okay. So for the moment, we're not quite there yet, but thanks. Yeah, so the anomaly, as I say, is once categorified. It's an n-dimensional theory because it's a map out of n-dimensional Bordisms. But as was indicated in the questions, in many cases, this is the restriction of a full n+1 dimensional invertible field theory, and that's how it's usually said. Okay. So that's the general picture of anomalies. Now let's talk about anomalies when we have a group of symmetries. So let's suppose we have a group. This could be a finite group, could be a Lie group, it could be some kind of higher group, homotopical kind of group. And supposing it acts as symmetries of some field theory, and our field theory has a particular dimension n, and it has some background fields. So what does it mean to say that a field theory has this group of symmetries? Well, the usual statement in physics is that means that we couple the theory to a background gauge field for G. So what's a background gauge field? Well, that's a connection on a principal G bundle. If G is a finite group, there's only a unique connection, so it's just the G bundle. So G bundles, they form a field, a background field, and I'm denoting that G bundles with connection as by its classifying space BG, but I'm putting the nobla there to mean that also these bundles are equipped with connections. And so we have our original background fields. They sit at the trivial connection, and what we have to do is extend both the theory and the background fields over this space B nobla G. So that is a typical picture of a group of symmetries in geometry as well, that you fiber something over the classifying space of the group. And so here we do that with quantum field theories. So we have a new space of background fields, and it fibers over B nobla G. So a typical example in physics, you might have a sigma model into a Riemannian manifold that has a group of symmetries. And when you couple, then, then you have a principal G bundle and you have a twisted family, a fiber bundle of those manifolds, and now you have a section of that fiber bundle. And at the trivial bundle with connection, that reduces to the sigma model field you had before. So now we're supposed to extend this theory, as I said, F, to a theory over this larger space of background fields. And now it has an anomaly, potentially. So let's suppose the original theory did not have an anomaly. And so what is the new anomaly? The new anomaly is some once categorified invertible theory, n-dimensional theory on this big space of fields, but it comes to us trivialized over this subspace of the original fields. That's saying the original theory isn't anomalous. And if we have that kind of relative class, then that's what's referred to in physics as an 't Hooft anomaly. Now, one way to get that is to have the anomaly alpha actually pulled back from the base. So if that's the case, then it corresponds to what would be a projective action of G. And so that's not the most general case, and it's easy to have examples of both types. For example, if you have a particle moving on a circle, and you have a theta term in that, where theta is a function, and you think of the symmetry of rotations of the circle, that's an example where it's not pulled back. The anomaly mixes the background gauge field and this function theta. But there are many examples where it's just pulled back from G. It only depends on the background gauge field, and that's the case that we think of as like a projective action of that symmetry, and that's the case that we're going to generalize to algebras of symmetries. So if G is a finite group, in that case, the anomaly is what's usually called the Dijkgraaf-Witten theory. We make a Dijkgraaf-Witten cocycle, and that's what expresses the anomaly, a cocycle on the classifying space BG. Okay, so now we come to algebras of operators. And I'll just point out algebras of operators in quantum mechanics certainly were there at the beginning. In fact, that's von Neumann in the late 20s and 30s was developing simultaneously quantum mechanics and the theory of operator algebras. So having algebras, which in particular have non-units, meaning non-invertible elements, acting on a quantum theory, that's nothing new. I think what's new is to call them symmetries. Anyway, so let's see what that looks like for a finite group. Instead of thinking of the group acting, we can think of the algebra, which is the group algebra. And if we have a central extension of the group, which is to say a projective action of the group, there's a twisted version of the group algebra. And the group and its central extension, of course, look very similar once we have the actual extension, the map, but the algebras look very different. So for example, if we take this group, which is abelian, then the group algebra is a commutative algebra. But if we take the Heisenberg central extension and we take its group algebra, then that's a matrix algebra, simple algebra. So they look very different, and just as algebras, there's no real way to say one algebra is a twisting of the other algebra, just looking at those algebras. All right. So these kinds of algebras we could think of as algebras acting in quantum mechanics. What's the analog in quantum field theory of abstract algebras and their actions? Well, that's what we call quiche. So with Greg and Constantine, we introduced this idea, which of course appeared in various forms in physics, but we abstracted this, this structure. And what it is a generalization, as I say, of abstract algebras from quantum mechanics to quantum field theory. What plays the role of elements in an algebra, which give operators in a quantum mechanical system, are defects in this quiche, and they give operators, so to speak, and other things in the quantum field theory. And the advantage here is that this quiche is located inside topological field theory. We have quite a developed mathematical theory now for TFT, and we can use that technology to make computations. So in particular, we can compute universal defects, universal relations among defects. All right, so what is a quiche? So it's a pair. Sigma is a topological field theory. If this is to act on an n-dimensional field theory, then this sigma is, again, a once categorified n-dimensional field theory, or we could think it's really an n+1 dimensional field theory. And rho is a boundary theory. It's called a right boundary theory because in terms of a module, if you think of this like an algebra and this as a module, the algebra acts on the right of the module. So that's called a right module or a right boundary theory. And, well, we use the word relative theory if this is a once categorified n-dimensional theory. The theory of that was developed by my student in his thesis, and that's the structure. And how does this act on a field theory? Well, if we're given a field theory F, then giving an action of this abstract quiche on the field theory is to give, again, a pair. We give a boundary theory now on the other side, a left boundary. And this, of course, this theory need not be topological, and this, of course, then need not be topological. And what we want is that the sandwich that we make this way, which is a kind of tensor product of a right and a left module over the algebra in the middle, that sandwich should be given an isomorphism with our original theory. That's the underlying theory. We write the sandwich in these two ways. So in other terms, we have an interval with sigma in the interior of the interval and these two on the boundary, and we're dimensionally reducing this n+1 dimensional theory sigma along that interval to obtain an n-dimensional theory. And that's our original theory. So this sandwich presentation separates out the non-topological part from the topological part. And then if we do defects, which we're not doing in today's lecture, but we can make a calculus of defects all inside topological field theory. Okay, if we have a projective theory or an anomalous theory, that means that it's sitting on the boundary of this alpha, which again might be once categorified n-dimensional or a full n+1 dimensional. And we can have symmetry in that case where rho is now a domain wall between alpha and sigma. Okay, I also mentioned that there's, in computing with these topological field theories and these boundaries, there's a world in which we can do a finite version of the Feynman path integral and extend it down to all codimensions. And those are called finite homotopy theories based on what are called pi-finite spaces. So if we have a finite group, or even a finite higher group, 2-group, 3-group, that kind of thing, with finite homotopy groups, then those can be computed in this way. All right, so finally we come to the new ideas. And that is the following question. If we have, and that's the question that was asked, if we have an algebra of symmetries rather than a group of symmetries, what's the notion of saying that that acts projectively? What's the notion of an anomaly? So we could ask the general question where it might mix with other background fields, or we could ask the one that we can address, which is what is a projective action? So how do we look at an abstract quiche and say that? And I already showed you just with a finite group algebra that we can't really look at the algebra and say that. It's very hard to say that just from the algebra. So that was the example there. So in fact, to answer that question, we can't do it in general for a quiche, but we do it for quiches with extra structure. And there's a geometric version of that extra structure and also an algebraic version of that extra structure. And it's only in terms of that extra structure that we can say when one is projective and the other is not. And in fact, that notion of projective, or the anomaly, is a relative notion between two of them, this extra structure. All right, so to explain that, I have to give you a quick preliminary about Dirichlet and Neumann boundary theories. Well, in PDE, like if you have a Laplace operator on a disk or something like that, the words Dirichlet and Neumann have a very baked-in meaning, stare decisis kind of thing. And, but in field theory, it's a funny carryover to use Dirichlet and Neumann, but it seems to be common. And, well, so what is the definition of Dirichlet? Well, I'm not going to attempt to give a general definition here. We want to give one in extended topological field theory. But one version of that is that supposing we have sigma, so sigma is an n-dimensional topological field theory, and I'm supposing it's fully local, which means we have all sorts of categorical data attached to sigma going down all the way to a single point. And now supposing that rho is a boundary theory. So that's the rho depicted here. Then we want a definition of what it means to say rho is Dirichlet. And whatever we say all the way down to points, it should and does have the following consequence. That supposing we look at this interval, which is rho composed with, after it's an adjoint, a kind of dual of rho. And here I just indicated some framing data, and that's what tells you that one end is rho and one end is this dual or right adjoint. And if we have this interval with these boundaries on both sides, this becomes an algebra. And here I didn't draw the framings, but here's the multiplication. This is the Bordism, the usual Bordism that gives you the multiplication. Here's the Bordism that gives you the unit of that algebra. So if we have this pair sigma rho and we evaluate on this interval, then if we're in some n category, this becomes an object in the loops HOM11 of that n category, but it becomes an algebra object. And if it's dualizable enough, then it defines, again, an n-dimensional theory, now with values in algebra objects in that n loops of that original category. And what we want is that that theory and our original theory, sigma, are isomorphic. And that certainly happens. Anyway, there's a condition which roughly means that, that this boundary theory, rho, is generating in some sense. So, some examples, if in fact sigma of a point is an algebra of some sort, then the regular module satisfies that condition. And if we have these finite homotopy theories, then in fact it's just a base point, if it's connected, that determines a Dirichlet boundary condition. Okay, in this definition, once we have Dirichlet, we can define Neumann relative to it. This appeared already in Clay's talk yesterday, and perhaps talks I missed earlier in the week, which says basically if we have Dirichlet on one side, then Neumann means that when we make this tensor product, this sandwich, we get the trivial theory. So if we have an algebra, what Neumann turns out to be then for the usual Dirichlet, for the regular module, is what's called an augmentation of that algebra. That has various words in different contexts. For example, in the context of tensor categories, that's what's called a fiber functor. Okay, but Neumann boundary theories may not exist. There are obstructions between them. Okay, so finally, what is the picture then? So supposing we have this quiche, and I'm assuming that the row that appears there is Dirichlet in the way that we said. So what is this extra structure? Well, we have to present this, this quiche as a dimensional reduction of something one dimension higher. So now this sigma hat is dimension n plus 2, and all of these boundaries are dimension n plus 1. And so what we should find up here is a quiche one dimension higher. That's a topological field theory that comes with its Dirichlet boundary. And it should also have a Neumann boundary. So it has to have both in such a way that when I make this dimensional reduction, then I get the original thing. So in the bulk, I'm dimensionally reducing this n plus 2 dimensional theory along this interval where I put this Neumann on both. If I put Neumann and Dirichlet, I would get the trivial theory, but I put Neumann and Neumann, and that is supposed to give me sigma back. Then on the boundary, we have this Dirichlet, which has dimension n plus 1. We have its boundary, which is a kind of interface between Dirichlet and Neumann. The Neumann condition tells us there's really a canonical one there. And that should reduce to rho. So once we have that presentation, then we can make a twisted version simply by, in this higher dimensional picture, having our original Neumann that was used to present the original quiche, that's here, and then we have a different Neumann condition here. So if we have a different Neumann condition, then it's the ratio of these Neumann conditions that's the twisting. And in fact, that then becomes an invertible theory, which is an anomaly. Okay, so that's a geometric picture of what it means to have a twist. And as I said, it's a relative picture. Okay, so when we have gauge theory, that fits in because a gauge theory can be reduced from a higher dimensional gauge theory with the same finite group or finite higher group. We have a usual Neumann condition, and we can have a Neumann condition with a Dijkgraaf-Witten cocycle. So that's a prime example of this. Well, there's an algebraic picture as well. And the algebraic picture is based on the following general idea, which is if I have an algebra A, then a twisted version of that is an invertible AA bimodule. So think of an algebra of functions on a space X. Those are functions on X. And if I have a line bundle over the space, then sections of that line bundle become a module over functions on the base. The functions are commutative, so we can think of it as a bimodule. And sections of a line bundle are a twisted version of functions on the space. So an algebraic way of saying what's on the previous slide is to say that this quiche has an algebra structure in some category of quiches, and a twisted form is an invertible bimodule over that algebra. Well, I'm being flashed all sorts of numbers I learned in kindergarten, but I've forgotten them. No, I think I better obey. So I was going to tell you how that looks with zesting of categories, but I'm afraid maybe I'm out of time. Is that what you're telling me?
Yeah, 20 seconds.
20 seconds. I will not attempt in 20 seconds to go through 3 slides that I laboriously wrote this morning. Thank you.
Are there any questions for the speaker?
So if I understand, the framework correctly, so the anomaly is always associated with the omega spectrum, which is
associated with a
omega spectrum, a cohomology theory, like a BG.
Well, so I said it's an invertible field theory or a shifted version. So let me interpret your question.
Yeah, that's what I mean.
A question about invertible field theory.
Yeah, invertible field theory is the omega spectrum. So in the dimension which I know really well, there's a subtle change of coefficient when you formulate the anomaly using this cohomology theory. In any model, the cohomology theory, in one dimension, the coefficient is a billion anyons. The other dimension is U1. How do you see this change of coefficient in this general framework?
What was, I didn't get, the change from something to U1?
So in the NER model, when you try to gauge, this is your definition of symmetry. And one obstruction lives in H-3 with coefficient in a billion anyons, and the other obstruction lives in H-4, which is a U1 coefficient. It's a very subtle change of coefficient.
Yeah, they're there on that slide I didn't get to. How do I see that? Well, okay, let me answer in the general framework. I mean, what's an invertible field theory? So an invertible field theory ends up being a map of, as you said, omega spectra. And we have a choice for what to take as the target, the codomain spectrum. There is a universal choice. And, okay, that's the spectrum. This picture is particular to fusion categories. And yeah, it might take a little work to make that anomaly fit the general picture of invertible field theories.
I have another question.
Sure.
Like in the physics community, we kind of understood that this Neumann boundary condition has the existence of the fiber function maybe 1 year ago, something like this. It's really hard to know when there is a module category with only one object. Do you have like a way to streamline the analysis? Because right now it's really, really complicated.
Yeah, so the question is there an obstruction theory given an algebra or a higher algebra? Is there an obstruction theory for having an augmentation? And the answer is I don't know of one. It's possible that there is one, but yeah, I don't know of a systematic way to analyze that question.
If I consider like the group algebra and say I give it a hop algebra structure by adding the coproduct, could I ask about sort of what classifies the anomalies for that? Would it be like this invariant cocycle defined on the hop algebra or something else?
You're saying if I consider the group algebra as an algebra,
that's right. Instead of a group,
symmetries on some, say, quantum mechanical system, how do I classify anomalies for that? Well, that's what I think I tried to say, that I don't know how to say an absolute way that this algebra is anomalous, this one isn't, this one represents something projective, this one something linear. We only saw a relative concept there.
Can I make a comment on that? Sorry.
So actually in my talk on Monday, I specifically talk about half algebra symmetry. And I think the right cohomology is you take the half algebra, you use that to tensor other things, and then there's a Davidoff-Yerta cohomology of tensor functors. That's the right cohomology.
One last question.
Thank you for the talk. And the starting point in all of them is some quantum field theory, and then you explore its properties. But often we are also interested in its relation to an underlying classical theory. And it's often the case that two different classical theories lead to the same quantum theory. How is this reflected? That's known as duality. So how is this reflected in your structure?
Well, that's not a question particular to anomalies or symmetries. That's fine. Was it?
Yes, it is, because the main point in all these dualities is that the symmetries and the anomalies should be the same, but the presentation is completely different. So I wonder whether, if you run your machine, will the two presentations will lead to the same structure, or will they lead to two different structures which happen to be the same in the end of the day?
Yeah. Well, another family of examples to think about is Chern-Simons theory in 3 dimensions for a torus group, where the classical theory is given by an integral lattice and a bilinear form, or a z-valued quadratic function on that integer lattice. And the quantum theory is given by a finite abelian group, the discriminant group of the thing you started with, and a quadratic form to Q mod z. And there are many, that map is infinite to 1 from classical to quantum. So that's another example without symmetry particularly, where you see that. So this framework, these Siegel axioms for Wick-rotated field theory, they don't have the fluctuating fields, but the classical theory also fits those axioms with the fluctuating fields there. And then there's a quantization procedure where you integrate out the fluctuating fields. And you're saying that we could start with 2 different classical systems, possibly with different fluctuating fields, but over the same background fields. Integrate them out, we get the same quantum theory. But this is just a general framework that's, in a sense, telling you what a theory is from some point of view, or describing some features of a quantum field theory. It's not getting into the details of that. So I don't think it addresses that question of dualities. Maybe another way to answer it is, it's the slogan, quantization is an art, not a functor. I don't think that there's a robust theory of quantization that's available to answer that question, let's put it that way. Still not happy with that answer.
This is my natural face.
Let's thank...
No further comment.
Let's thank Dan again for the nice talk.